Uh, Thank you for the kind introduction, Ricardo. It's a pleasure to be here. Great. So, as was mentioned, this is, as it happens, 50th anniversary of the first publication on a sort of a practical way to do magnetic resonance imaging by Paul Lauterbur, which had long-lasting effects. So, just to give an overview of the talk, first of all, it's going to be non-technical, no equations, no density matrix formulations or anything. And so I'll start off with just some of my own background, which Ricardo's already summarized. Talk about some of the early steps that led to magnetic resonance imaging, because NMR per se had been around for some decades already at that point. Then some of the technical issues and all that came up in the early days of MRI, as well as some of the early applications and how it's evolved. Then sort of shifting gears a little bit to say, how did we move then from sort of what radiologists traditionally have done, which is look at pictures to try to extract quantitative information and find sort of meaningful data from those images. And then talk a little bit about some of the recent advances, so you can look at the posters and get a more up-to-date view of that. A little bit about outcomes research, which is in the modern world becoming important, trying to involve looking at the evolution and significance of any imaging studies, and some of the remaining technical challenges, and on the other hand, some of the opportunities there. So, as Ricardo's already summarized, I did my PhD in astrophysics at Princeton, where you learned, though we'll hear later, there are a lot of parallels between medical imaging and astronomical imaging. I've learned about image analysis. Astronomers are some of the first people to use high-density image sensor arrays and Fourier methods, which are at the heart of radio astronomy methods. And then did my medical training at UCSF, where there was, as Ricardo mentioned, a strong interest in the sort of evolving technologies. So I was there during my residency and training. Digital imaging was really being introduced. New CT methods. I injected contrast agent on the patients in the original Mark I water bag CT scanner that translate rotate, and we had some of the very first MRI systems there. And while there, I got to use an early small bore MRI system while they were waiting to build a whole body when looking at some T1 effects of oxygen going back to small bore and Linus Pauling. And then I moved to University of Pennsylvania. Was there for about 20 years in the radiology department. And was building, initially I had trained in CT and ultrasound, but then switched over to MRI as that became a viable clinical tool. The very first NMR meeting, it was still called NMR at that point, was in Winston-Salem, 1981, which was actually a year before the first SMRM meeting. In 2001, right after the 9/11 events, I switched up to NYU following Bob Grossman, and I've been here since. And my clinical specialty, as well as research, has been focused on cardiovascular MRI. It's involved, as I mentioned, some of the early societies. There are two sort of competing NMR societies or MRI societies, the SMRI and the SMRM. The one was a bit more technically focused, the other more clinically focused, but they were later merged to the present-day ISMRM. I was also involved in the formation of the sort of a specialty society, the SCMR. And there was a lot of jockeying around for positioning. This is clearly an evolving new technology. Who is going to control it? Nuclear medicine people said, whoa, it's got nuclear in the title. And cardiologists wanted to do the cardiac imaging and so on. So that's still to some extent playing out all these years later. I was on my chairman at the UCSF was Alex Margulis, who was sort of the godfather of radiology at that time. They said that we in charge of the AZR NMR committee, American College of Radiology. And so one of the things we were trying to do is standardize the nomenclature, which was sort of all over the place in different publications, just trying to people use a consistent way to denote things. And so particularly we proposed MRI as so dropping the nuclear, which was sort of threatening to a lot of people, as well as being a convenient thing to do. In the course of my work, I've got to meet actually many of the Nobel Prize winning MR and MRI pioneers, Paul Lauterbur, Peter Mansfield, Richard Ernst, Felix Bloch came through in a visit, who was an early NMR center. I was pleased to see actually the clinical utility of the old work. Purcell came through, met Kurt Fruchtig, and so it was interesting. Unfortunately, none of their brilliance rubbed off on me, but it was fun to meet them. So what is NMR? A lot of people here work with it, but not everyone. So it's the phenomena really known from physics back in the early 20th century, really. And there's sort of a few key parts that nuclei in our body and hydrogen, which is 40 molar or something like that, can be magnetized very weakly, but collectively magnetized in a strong enough magnetic field. So collectively, we have this sort of nuclear magnetization, which by itself you don't really see, but it also exhibits this resonance phenomenon. So if we put an oscillating magnetic field at just the right frequency, we can induce the magnetization to rotate away from its sort of preferred direction along that strong field. And if you sort of leave it there, it doesn't just get remagnetized, it starts precessing around. So that bulk magnetization is like a spinning magnet, and it's like a little generator. You hold a coil up, you can actually get a detectable voltage, and that's our signal. Weak as it is, it's very detectable, and it's a very specific frequency depending on the field. There's a couple of relaxation times which are associated with that, which are very handy for imaging. There's a so-called T2 relaxation time. The signal doesn't last forever, and it's not surprising, nothing of those. So that characteristic decay time is, again, dependent on tissue state and then affects the signal strength. And T1, which is how long does it take to get remagnetized? Again, that depends on the local state. Now, these phenomena were well known well before use in imaging. In particular, chemists had taken advantage of the fact that the resonance frequency depends on the field strength at the nucleus, but that's affected by electron orbitals around. So we have a so-called chemical shift, which is used to use both analytical and structural analyses in chemistry for decades before imaging. So how do we get from there to imaging? Well, the basic phenomena I said have been well understood. First described by Rabi in the molecular beam experiments over Columbia in the 30s, and then Bloch and Purcell, working independently in Boston and at Stanford, was able to demonstrate the phenomenon in bulk solid material or liquid material. And all these got Nobel Prizes because this is really fundamentally important. But also, people had also noticed there were interesting biological effects from these NMR signals. If they put little tissue samples in instead of little standard chemical sample, if you move things around in the test tube, it changes the signal. The relaxation times are different in tumors than they were from normal tissues. You can measure diffusion and then look at the effects of the tiny little random walks of water, and it'd be in a C cell where it's a restricted motion to actually detect those differences. Now, Damadian, who was a character at Downstate, who was very bright but very abrasive, suggested we could try to link position in the NMR signal by having sort of a sweet spot in a magnet and sort of move people around. But that was sort of not a practical way to do imaging per se. So the first real imaging was proposed by Paul Lauterbur. This is around the time people were first developing CT scanning. And they had the idea, which we'll talk a bit more about, which is that we could use the magnetic field control device that is built into the spectrometer to actually create images in sort of inside-out way of doing it. He drafted a patent disclosure about this, which I've actually seen, and Joan Dawson, his wife, had published a nice book on it, which includes that, which had many potential applications, but the State University of New York, in their wisdom, decided it was a waste of time trying to spend their money on such a crazy idea, so he just went ahead and published anyway. So he was always scrounging for time in the local radiology MR systems after midnight, where Peter Mansfield on the other side of the Atlantic was able to donate a magnet to the local hospital. But the main thing was that the CT approaches were very useful. We still use them, but instead, what people do in practice is mostly so-called Fourier domain approaches, which we'll talk again a bit more about, which you find here by Peter Mansfield and Richard Ernst, who was working on the basics of nuclear magnetic resonance and had proposed actually the method that we actually now use. We'll come back to that. And the big thing about MR is that we have many sources of image contrast. These different relaxation times, just the amount of stuff locally, so all these contribute to being able to see structures that are otherwise very difficult to see, and that's very powerful. And that's why NMR has become such a good clinical tool. There's just so the Nobel Prize picture. As that Paul Lauterbur and Peter Mansfield got the award for imaging per se, but Richard Ernst had separately gotten a Nobel Prize for using the pioneering developing the so-called Fourier techniques for the NMR spectroscopy. And he'd actually published the method that wound up being used. It's only a couple of years after Paul's. So here's a couple of pictures from the original article, well, 50 years ago now, wherein the idea was, how do we make pictures out of this, where things are in the body? It was not at all obvious. The tools were there, the pieces were there, but no one had ever put it together. And so what Paul came up with was basically to say, instead of doing a spectrum in a conventional spectrometer where we have these extra magnetic fields to try to make things as uniform as possible to keep the lines from being blurred, we're going to take and just do one single line, which is water, which is very boring, one line, but then actually deliberately make the field non-uniform in a controlled way. And so now, depending if we have this little phantom with a couple little tubes of water, and apply these magnetic field gradients, which are part of the shimming system, normally make the field uniform, make it deliberately non-uniform. If we apply a magnetic field gradient perpendicular to the line between these samples, then they'll be at the same magnetic field and make one simple line. On the other hand, if we apply a gradient along the direction between the tubes, now they're in tightly different fields, depending on their position, and now we get a spectrum. So it looks like a spectrum is really all water, which shows these two separate lines. And as we change the orientation of that field, just mixing and matching nominal x and y, we can make a set of lines that are dancing around, and he just made a simple CT reconstruction algorithm that is able to reconstruct a hand reconstruct images of those two tubes. But as I say on television, but that's not all. He also then said, well, what if we dub the water in one of these tubes and change its T1 relaxation time, then change the power of what we're doing, and now we have relative intensities which depends on the power. So we have imaging of T1. And so he actually was doing T1 weighted imaging. And then the contrast agent is really messaged by being able to absorb that water. So this is really quite an interesting article in that way. It's a little 2-page technical note with a lot in it. And here's just an extract from that. He points out that we can go from 2-dimensional to 3-dimensional imaging, we chemical shift imaging, we do diffusion imaging, and other. And so, in fact, that all did come to fruition. So it was a really quite an important paper. So this is a sort of a schematic diagram of a conventional clinical imaging system. And the basic idea of Vladimir is really what's behind it all. We can code position through the linking of local magnetic field variation with position to frequency, and then use frequency to encode position. And so in the original article, he proposed the term zoigmatography, which never caught on, but basically derived apparently from a Greek word that's a yoke, like the yoke, the oxen pulling the plow across the field. So the gradients were linking position and frequency, enabling us to create images. And so using gradients in different directions and different strengths, we can actually encode enough information in the data to reconstruct the images. So we typically have to do this multiple times in order to get enough data to actually make an image. And gradients can also be used for a variety of other things. We use them to select the imaging region, not part of the original paper. And so this is what we see in this imaging system. We have the very strong magnetic field just to create the magnetization that's going to be used to do things. We have RF and gradient coils to create the excitation, to detect the resulting signal, to encode position, and all the social electronics to drive those, and a computer or multiple computers to run everything and do the image reconstruction. Finally, all this is enclosed within a room that's designed to screen out any artificial external interference, because the signals are very weak. And so this is the paper that got me interested in MR. It came up from the Aberdeen group with Gail Adelstein and Tim Hutchinson's group. And this is a picture of the heart. And I got really excited about that. So you say, well, I said hardware checkerboard, but this was really neat that we could actually see this with no contrast agents, anything. And so we see the left ventricle, the right ventricle, the aorta, and some vessels in the lungs and so on. And this is the diagram from that of the so-called spin warp imaging, which instead of having a rotating set of gradients, which sort of like having AP and lateral and oblique images in a chest X-ray, we actually have use of gradients to encode position. So we have an excitation pulse here designed to create the signal. We have slice selection by applying a gradient during this excitation time, this sort of nominal y direction. We'll have a gradient imposed during the signal detection, which is just so-called frequency encoding, which is the heart of things. So our signal is detected down here, and the signal variation is a function of time, then can be put through something called Fourier transform to get the equivalent set of frequencies, which again, because of the gradient, it maps to position in a very nice way. So this is really just a projection along this x direction. And then instead of having a rotating set of gradients, before we do this gradient detection, we do a variety of repetitions to experiment with different strengths of the gradient along the orthogonal direction. And so mathematically it winds up this is the Fourier transform in real time, and this creates sort of a set of kind of pseudo-time samples in the other dimension. And again, we could just make a nice picture using the Fourier transform. So The important part of it is not just that we can make a picture, but they make pictures that have the signal that depends on local tissue state. And that's the real strength of this. In addition to that, we can add contrast agents, which are designed to be chemically very inert, but to change local relaxation times depending how they get delivered. So that's really a very powerful way to make images of showing different pathologies. You can also use these gradients to do things like encoding motion. We do pairs of gradients, so it sensitizes to bulk flow or to diffusion, depending how we're doing things. Unfortunately, local gradients like for metal or iron deposition will affect the images, but that can actually be turned to our advantage of the local microgradients that are coming from the brain just because of different oxygen saturation of the local blood within the tiny vessels actually changes the signal in ways that depend on mental functioning states, which are very, very powerful. So in order to get this thing going, we had to have strong magnets, to set up this resonance condition. And initially, we had when we first had the system at UPenn was just built on around a Walker electromagnet at 0.12 Tesla. And then people experimenting permanent magnets, they had strengths and weaknesses, but everything sort of converged on superconducting magnets. The superconductors have this unique kind of quantum effect that they have zero resistance. So it's only resistance like where you join these wires together. And so once this very strong magnetic field is set up, it keeps circulating. So you don't have to worry about continuously applying a large amount of current, and those doesn't generate a lot of heat that has to be dissipated. There were a lot of issues that came up though. So what strength to run these magnets at? And this was a source of great contention. It became a marketing issue. So for example, I was at the floor of the RSNA one year when Paul Bottomley, who was with GE, was advocating 1.5 Tesla, and Leon Kaufman from UPenn, who was also from UCSF, was working with a different company, thought it should be around 1.3 Tesla, and they almost came to blows. Literally, I saw this being held back by their seconds on the floor of the RSNA. It was dramatic. That's the only time I've seen people coming almost to blows over some point of technical issue. But there's, obviously we have very strong magnetic fields. You can't have people with pacemakers wandering by them during sighting issues. These things are heavy. And so these are just sort of practical issues that came up. The RF coils initially started off with spectrometers, just simple solenoids, were replaced by surface coils. And some of my original work was we're trying to work on surface coils. They get turned to surface coil arrays, which Dan then exploited for being able to accelerate the imaging. Gradient coils, again, were important, as I said, so for both the position encoding and slice encoding, as well as a variety of other things. They're just really kind of the Swiss Army knife tool used for MRI. And so the various methods would try to make them more linear, make them switch faster, so that self-shooting gradient coils. And this is all important, hardware development to make this possible. Of course, imaging and reconstruction methods. The original imaging was basically radial with a full lot of room. We've come back to that for some purposes in recent years. But this so-called Cartesian case-based sampling, where we're sampling essentially the Fourier transform of the image we're trying to create, and as a much more mathematically convenient, we do that in a nice rectangular grid. But there's a whole variety of spirals and cones and other sorts of clever things people are working with. Electronics initially was all analog, and it all drifted and had to be recalibrated. And eventually that evolved into much more stable and flexible digital imaging. So that was a real key part of sort of making all this happen more reliably and flexibly. Contrast agents were developed, as I mentioned, which locally shorten the T1 time, thus increase the signal strength depending on your imaging. But the earlier agents turned to have real health problems, particularly in patients with renal failure. And those have since been replaced with more stable agents. And there's still some concerns for patients with renal failure, which is not uncommon in patients. And finally, there's a lot of power, even the superconducting magnets that we use to supply everything that's in the system. So people now with a concern for climate change and that, trying to do this in as green a way as possible, turn things off at night, not running the magnet. So what was this used for? Well, imaging in general has really three purposes. You first think about diagnosis. Can we find there's a tumor there or not? Or what kind of tumor, for example? But it's also very useful as well for planning. You know what's there. The surgeons have to know, well, how do I going to approach it? Is it something that's surgically approachable or not? And then finally, you're treating somebody, the symptoms by themselves are not so reliable. So imaging is very helpful for following up. Is the treatment doing what it's supposed to? And a big advantage in MRI is the imaging method. Is there's no radiation, no ionizing radiation, which makes it very safe. It's very flexible. We can use cross-sectional images in any plane without worrying about things like acoustic windows or ultrasound. And it gives us a lot of information on structure. but also it gives us information on tissue characterization, not one-to-one map to say this is this, but it's certainly very helpful for trying to differentiate the things that might otherwise look quite similar, effects on function. And so we can see things like tumors, areas of ischemia or infarction, inflammation, degeneration, trauma, and on and on. It's just a very remarkably flexible tool. So for early applications, particularly looking at the brain, spinal cord, which are otherwise very hard to look at, even peripheral nerves and musculoskeletal system, people used to be using x-rays, which are very nice for looking at the spine and bones, but you can't see what's inside the joints. You can't really see muscles well. And MRI has turned into a very powerful tool for that. Body applications lagged a little bit because the imaging had to be fast enough that the patient could hold their breath. Otherwise, the imaging would not be clear. And so the real advances in body imaging came with shortening of the imaging times to make that practical. Of course, pediatrics, the absence of radiation is very important. And breast imaging, we can see masses, and we can see the shape of the mass, we can make contour, look at contrast enhancement, all that's very helpful, trying to differentiate what it's likely to be. My personal area is the cardiovascular imaging. And although this was very promising initially, that's the first thing that got me interested in the field was Bill Edelstein's paper. But it was really slow to really have a clinical impact, and it's still increasing. So there's a lot of heart disease out there, there's not a lot of cardiac MRI, but that's increasing now. Spectroscopy was where everything had come from. People thought, well, spectroscopy is going to be a big area of application. We'll do non-invasive chemical compositions of different tissues. Turned out to be not so easy. There are niche areas, kind of spectroscopy of certain brain tumors or something. But it's surprisingly not turned out to be a major clinical outcome. So this is another paper that caught my eye when it came out from Graham Bitter in 1982. He was taking the same patient. On the left, we see a conventional CT. We see, well, we can see some ventricles. We can see some gray and white matter in the shading in here. But those are not really seen particularly strikingly. But then doing an MR image of the same location and varying only the sensitivity to T1, we see dramatic differences in the appearance. But white matter is quite clearly shown as being bright or maybe dark if you just change the T1 weighting. And this is something that was really quite dramatic, how much we could really change the appearance with a simple changes in the instrumental settings. And so with even though we could see this with CT, the amount of signal change here is really minute compared to what we can do with MRI. So just an example of the sort of things people can do these days is that we've got much higher resolution in this paper here and normal subject, but this is really only down to 1/4 of a millimeter isotropic. And you can see really as we go progressively higher resolution, you can really refine details. Now, to do this, we have to get enough signals noise. You have to put quite high fields, and people have to be really. You can't immobilize someone to be that well mobilized. So you really have to build motion correction to the imaging. But it's really remarkable just how far this is coming. More mundane applications, things like musculoskeletal MRI. Here we have an example of someone with a simple tear in the meniscus, not uncommon injury. And MRI is really very flexible. We can choose a plane to show it, and we can do this. This is done on a routine basis now at a variety of areas of application. And some trauma, tumors, edema, and so on. Another paper that caught my eye when it came out was this paper from Ray Kim's collaborators, and for cardiac imaging, we're using contrast agents. And although people had noted, back a decade before, that contrast agents seem to get picked up in infarcts, he really did a very thorough job correlating that clinically and in animal models of infarcts. And we can see here an example where the contrast agent is accumulating this little dark area here. The non-reperfused infarct is quite large, and a reperfused infarct is much smaller. And then let's look now in ex vivo, we can see those same areas enhanced, but then we do supervital stains and show which areas are live and dead. And that really correlates remarkably well with the imaging enhancements. This is really put cardiac imaging kind of on a very solid ground to say that the areas of infarct we see are in fact areas that are irretrievable muscle, and they're very helpful for clinical planning purposes. This is some of my early work. You can see how with conventional cardiac MRI, it's really quite nice. We can see a lot of structures which were not at all visible on those earlier images. But in addition, we also notice everything looks the same. It's all gray. We can't really say much about that. So this is a normal volunteer with our little tagging techniques, which we did a long time ago. We can see that now we can reveal motion within the heart wall, which is otherwise really invisible. There's no other way to do this. Now, this is a neat technique, but we're still trying to develop efficient and robust method to analyze the data. And so that's a continuing work in progress. Diffusion weighted imaging is, again, an area that turned out to be surprisingly useful in some sense. As was mentioned in the early days, we could see already in things like yeast cells, we can measure diffusion and show the effects of tiny structures, and we'll hear more about that later. But it was surprising how much difference it was, for example, in a stroke. A very early stroke, the conventional MRI image looks almost really normal. But with the diffusion, we can see that the diffusion is markedly impaired in the area of the stroke, and this later will turn out to be more clearly visible on conventional imaging. Similarly, in cancers, for example, or infections, we may have local alterations in diffusion, which can make things much more apparent than would otherwise be very similar to surrounding structures. So these images are really neat. They're very clinically useful, but the question is, can we go beyond that? Conventionally, radiologists have mostly been pattern recognizers. And so, but there's a lot of information in these images. And having a background in astronomy, I saw images as this masses of arrays of two-dimensional and multidimensional data instead of just things to pattern recognize. But there are challenges in trying to do that. The images are totally, sort of arbitrary units. There's no calibration. There's no thing equivalent to so-called Hounsfield units in CT. The images have a lot of shading in them typically, which visually doesn't bother you at all. But we try to make a number from that segment on the basis of the image intensity. It fails because of that. And there's a lot of nonlinear there, signal effects. You double the dose of contrast, you don't double the signal. Low signal to noise is, of course, fundamental in anything we're trying to quantify. But there's still a lot of potential for trying to do that. We can address all these issues. A lot of recent attention has been paid on measuring relaxation times, not just taking advantage of their effects on the image. So these are sort of simple scalar numbers you can derive. What is a T1 and a T2? And does that change in some characteristic way that reflects the disease? We can look at the contrast agents, which again are changing. Instead of just visually assessing it, we can measure the effects of contrast agents, say, in the first pass into the tissue, which assesses perfusion, so we can actually quantify regional perfusion. Look at the accumulation of contrast agents later on, get an idea of the distribution into the extracellular space, which is where the contrast agents wind up going. There's a lot of information in there, which we can quantify, not just eyeball. Chemical shift in spectroscopy, as I said, there's a lot of early interest in that. Fat and water, which are different by about 3.5 parts per million, are really pretty easy to separate, and there's lots of those signals. But other things like the phosphoprete and things like that are much lower signal to noise. And that's really been a problem trying to turn that into clinical applications. Magnetization transfer is another area that was of great interest. We can exchange magnetization basically with the spins with the surroundings, looking at so-called bound and free water, which those are real effects. They're interesting, but they turn out not really to have much practical clinical application. But there's a whole variety of other ways people are still exploring T1 rows and so on. Now, in addition to this sort of scalar characterization of tissue, we can talk about vectors. How are things moving? What directions are they moving in? Flows, for example, emotions within the heart wall. And so that's another interesting area to explore. We use that on a daily basis in the clinical imaging just to assess flow down the aorta and pulmonary artery, for example. We can go beyond that to sort of tensors, so-called, where diffusion is not just a local vector, but it actually depends on the orientation you're considering. Or in the case of strain in the heart wall, at one location within the heart wall, it's thickening radially as the heart is contracting, but it's also shortening in the other dimensions in order to enable that thickening. And so that becomes a more complex kind of data to get. I'm not sure how to best turn that into clinical use, but it clearly has a lot of information that's more than just a simple bulk motion. And functional MRI, of course, had a huge impact on the understanding of neuroscience, because we can actually see now the effects, small as they are, and they're real, for the changing the blood flow, which has indirectly been reflected in the signals that are moved. So again, this is something which is the challenge now becomes, how do we design a suitable protocol to do the challenges to do this? And just a sort of a misquote from Marcel Proust, a famous quote, basically saying that the real voyage of discovery consists not in seeking new landscapes, but in having new eyes, new ways of looking at things. And MRI certainly provides us a wide range of tools that really give us new eyes. So just some examples of where quantitative imaging is playing a role. Things like perfusion imaging, as I said, is very promising, though it requires extra steps to do that. So eventually we mostly use visual assessment of things, but the numbers are interesting to try to get. Functional MRI, as I said, has really been a very remarkably flexible tool, though it's still in evolution. Diffusion brain mapping for looking at the diffusion along fibers. I'll show you some examples of that. T2 star is a sort of a measure of local field and homogeneity related to iron deposition, which actually changed the clinical management of hemochromatosis patients with beta thalassemia. Get measure what's the state of their heart with the iron, and that can decide how to change that. It's actually changed the demographics of the disease. I'll show you some other examples. So it's just an example of the kind of information you can get with functional MRI in the early days. So the first things they did, flickering checkerboard patterns or something, and watch what happens back in the occipital cortex, which we'd seen a very lovely talk on yesterday. And you can do these very small changes in the signal with different tests, so it needs very careful analysis and sort of specialized statistics to decide what's real and what's just not. But we can superimpose those data on underlying images. And again, you can see here on the occipital cortex, we're getting lighting up on both sides, and it all depends on the particular paradigm that we pursue. Here's an example of work on trying to map diffusion patterns, and even those motions are only sort of microns. We can actually use that anisotropy of the diffusion to now map. This is composite data from multiple subjects, different patterns of the fiber tracts going different directions in the underlying nasal nuclei are within the brain. And this is now being explored. And then we can then combine this information with functional information and so on. This is a clinical example of 4D flow, which turned out not yet to have any major clinical impact. This is a patient we had with a left superior vena cava sort of anatomical variant, which normally just dumps into the right side of the heart by an indirect route. In this patient, it actually went right into the left atrium, which was not where it's supposed to go. But the patient was not desaturated. So the question is, what was going on? Is there a risk of stroke? How can we assess that? So here's this, again, cross-sectional imaging, again, the flexibility of MRI to choose arbitrary planes. Then we did 4D flow in this extra little tube here and showed that the flow is dominantly up, not down. And so that's why the patient was not desaturated, and they could sort of not worry so much about emboli. So where are we going? Well, there's a lot of things left to be done. A big area of application has been doing more with less. So the watchword of the 21st century. So particularly, can we undersample the data and still get decent pictures? And then to speeds of acquisition. So as I mentioned, Dan had done a lot of work in parallel imaging, so-called using the different response patterns of having these multiple arrays of coils scattered around the body, using that to sort of disambiguate what would otherwise be undersampled problems. And compressed sensing is another area that Dan's worked on, and a number of other people who've done some work on using the fact that images that we create typically are not random. So if you look at the electrical engineering literature, it says, well, you have to sample so much data in order to reconstruct a given sized image. But in practice, because there's a lot of correlation between the data points, you can actually get away with sampling a lot less data and still create a decent image. And then that's been extended further, so-called multitasking or subspace analysis, using not just this conventional imaging data at dimensions. We can do all other kinds of dimensions and still acquire much less data than you have to if you had to separately reconstruct each individual image in that large cell or pattern of cells of different images. And so that's become a very powerful tool. And of course, machine learning is so ubiquitous these days, and it's being applied for reconstruction, where we can sort of automatically learn how to reconstruct the data from different the images from different kinds of data, as we heard about yesterday, and the various of machine learning approaches to image analysis, for example, automatically segmenting and detecting and classifying diseases of various sorts. And then something I'm interested in that we can try to use machine learning perhaps to do pre-processing of very large data sets we get to find where are the salient regions and bring that to human attention. Of course, there's a lot of ongoing technical developments, and imaging hardware continues to get better. Computers keep getting more powerful. And then people start now integrating MRI with other kinds of imaging, like positron emission tomography. We have a PET MRI system here, and integrating them with which we will soon have with a linear accelerator for radiation therapy, so we can interactively guide therapy with the concomitant use of the MRI. It's an evolving new area which is going on. Here's just an example of another paper which I found really striking. Anthony Christodoulou in California, where they do cardiac imaging now and extending some work we had done on sort of simultaneous cardiac and respiratory reconstruction of the images of the heart with free breathing and continuous data acquisition. They sort of extended that. We can add in now a sensitization of T1 and T2, and they can throw in a contrast agent, watch the dynamics of that. So this is, we get a very large data set. This is just a slice through it with the T2 dependence, the T1 dependence, and very large data set, both still undersampled compared to what would need to be really reconstructing that all independently. But now we can separately make images to say T1, T2. We can slice through the heart along this dotted line here, and here at this sort of bars, so the heart contracts and relaxes. There's a huge amount of information here, and it's all interrelated, and there are correlations between all these, which make it tractable to do in a reasonable period of time. This is an evolving area, but I think very promising. So shifting gears a bit, I just want to think a bit about a different issue, which has become also very important in the 21st century, which is, well, that's very nice, but what can we really do with it? Does it really have an impact? And that's really become a criterion for anything like you want to get your new study funded, or you want to get even funding to do research on it. You have to show that there's likely to be a significant impact on clinical outcomes. And the early studies we did in clinical MRI back in the early days, isn't this neat? Let's start it up. Were really then 10 years later heavily criticized. They weren't sufficiently data focused. In our defense, we said, well, we couldn't really practically do standard things because there wasn't any standard thing. Everything was evolving. The machines were different every few months. And it's also hard to link the clinical outcome to one particular imaging exam as part of a complex patient evolution. It's also expensive to run large-scale imaging studies. Let's do 100 patients with and without the imaging and see if there's outcome differences. And then finally, the images are really neat and striking, and things like magnetization transfer, for example. It's really interesting, but you have to have that clinical utility for anyone to get excited and to get the studies reimbursed. And so that becomes a whole issue. There's a whole field now, outcomes research, and various ways to try to show that there's meaningful outcome. For example, if you could show that if we can individually tailor therapy, so people that otherwise might look the same, but have different underlying pathophysiologic states, we could actually tailor the therapy and get better outcomes. So that's something which is really important to show that that's justified to do that. Or if you can reduce the need for other imaging modalities, we can do one shopping, as was sort of used as an expression at times. But ultimately, all these are ultimately tied to cost, which sort of like prosaic and boring, but this is real. Whether the direct cost of the imaging or associated costs, say by not having to do other imaging or having patients with improved quality of life here, different things that are quantifiable. Now, what about challenges? Well, equipment is still very expensive. It's millions of dollars to buy and install an MRI machine. So it's tough to put in a clinic. And the imaging itself is time consuming, and the analysis of those images is time consuming. You have to pour through a lot of images. And that also adds to the cost of the exam. There's still a variety of artifacts. Motion is a real bugaboo in cardiac imaging, for example. People have irregular heartbeats, so they can't hold their breath. The images are significantly degraded and limit their ability to assess them. And a variety of other things like metal, like people have implants of one sort, and there are other sources of field homogeneity, even bubbles of air in the gut can cause problems. But the gradients we use are still not as linear as we'd like. So there's various artifacts that have to be dealt with. It's also still problematic to really get reliable pathophysiologic data. The issues of quantification, having to deal with very high dimensional data sets that have to be analyzed. There's a whole lot of different factors interacting. And as I said, this is remarkable. We get such good pictures of the study that's inherently such low signal to noise ratio. But all these are opportunities. The two sides of the coin. A challenge is also an opportunity. And so if we can bring down the cost of MRI, and that's happening now with the hardware, people have heard about people going to lower field systems, back to the future, reducing the number of personnel costs by making things more automated. So we can use machine learning to try to set up the exam and do the protocols with just someone helping run it from a higher level. Clinical personnel. Again, if we make the images easier to read, then that you don't have to be as skilled, you don't need as many people. And citing, again, lower field makes it easier to cite, and that's part of the cost. And particularly keeping the exam short. It's easier on the patient and also bring down the cost per exam. And if we can do all that, we can really increase the access to MRI. We can introduce the access to MRI for patients disadvantaged in the cities who don't have access readily. Rural patients who, things are too scattered now, they have to get to an academic center. Internationally, of course, in Africa, for example, there's maybe only a few MRI systems per country in some places. And so if we can increase the access, we can bring the benefits of these increased diagnostic capabilities to a wider range of people. And finally, the data that we do get, if we can make things more quantitative, extract more clinically useful data, then again, machine learning has great potential there, that it's still under development. So we have to worry about how we train those machine learning. We want to build biases into our algorithms. And going forward, we need to really better correlate imaging with outcomes in order to have that data put into the machine learning algorithms. So in conclusion, MRI's come a very long way from its early beginnings. Paul's work 50 years ago was very prescient, and I said he understood where a lot of this was going, and he did a lot of the firsts of those things who often didn't follow up on them. It really provides a remarkably rich array of different kinds of information that really no other single imaging technique can compete with. It's benefited from both hardware and software research and development, and those developments are still ongoing and things are continuing to improve. So, but while it's already now become a very major clinical tool, there's still a lot of challenges before it can really achieve its full potential. I don't think in any way we've sort of come to the end of what we can get out of it. And I think that there are ongoing advances in MRI research, as you're hearing about at this conference and elsewhere, that provide us that we'll have an even greater role for cardiac and other kinds of MRI in the future. Thank you.
Thank you, Leon, for the great overview. Are there questions, curiosity from the audience, Camille?
There's a real pioneer.
Thank you, Leon, for that very interesting talk. I was intrigued by the spin warp diagram that you showed by Edelstein's paper. I had not read that paper, and he starts with an adiabatic half passage before he plays out the sequence. And I mean, I can imagine all sorts of reasons why that can, be good, contrast this and that. But do you know what was the rationale for doing that?
I didn't comment on that. That was one of the other little wiggles in that diagram,
At the very,
which is before the excitation. There was that case was the adiabatic passage. You could also, but nowadays we do that with, say, just a simple inversion pulse. But we're still, in fact, using, using Mike Garwood's more robust kinds of inversion pulses to try to do the inversion. That sets up a condition. It sort of does by itself doesn't make a signal, but it alters the state of the magnetization. Right. So then, if we wait a little bit, depending on local T1, we can get increased contrast. And so that sequence actually includes the T1 weighting. Using that,
so they were thinking about T1.
So just very much contrast built right into that original paper, and sort of following up with the work that Paul had done initially with the dope sample.
Interesting.
So practically, otherwise, if you just image the amount of stuff that's there, you get a very gray image. You really, the amount of water differences between a tumor and the surrounding normal tissue is, just a few percent probably. And that by itself makes it boring images. And you really need T1 and contrast to that to get the kind of pretty contrast that we see in conventional clinical applications.
I have a good question. So you mentioned cardiac MRI as picking up again, as cardiac MRI is becoming more popular. What field strength do you think is going to be the ideal one? Because there are people trying at 70, 3T, but it seems that 1.5 is still the best one.
So the question is, what's the best field for cardiac imaging? And just like that early debate on the floor of the RSNA, that's still a vexing issue. The higher the field you go, the higher, in principle, the signal to noise can be. And so the small things, like you saw that remarkably beautiful pictures that I think that was 17 great. But and we'll hear more about how we can even go higher. But the higher you go in field, you have other problems. The relaxation times change. T1s tend to get longer, which means that you otherwise might get weaker signal. T2s get shorter. Again, you have less time to take your data. And the field homogeneities which are produced by the body itself and homogeneities become worse at higher field. That scales directly. And so there's a lot of technical challenges at higher fields which have to be overcome. So for practical clinical applications, and people often tend to want to stay around 1.5 Tesla rather than 3. We do clinical applications on both, but it's often technically a little easier for a variety of reasons, like trying to synchronization with EKG and that to be at the little lower field. It's an evolving area now, and companies are exploring reintroducing lower field systems that are easier to cite. And for some applications like cardiac may actually be easier to apply. So you pay a little penalty and sit with the noise ratio, you gain a lot of operational simplicity.
Thank you. Are there any more questions? So then thank you, Leo, again.